Hey you guys, this is Mr. Sal. We're going to go over a quick lesson on proportional relationships. Take 1 minute and write down the objectives. So I know how to find a proportional constant, and I know how to tell if a table and graph represent a proportional or proportional relationships. We'll also look at writing equations based on the proportional constant as well. In this chapter, you will learn how to write an equation that has two variables to represent a situation. In addition to writing equations, you can represent real-life relationships in other ways. In 6th and 7th grade, you studied proportional relationships and represented these relationships in various ways. The problems given below will help you to review how ratio and proportion can help relate and represent mathematical quantities from a given situation. So number 1, Julie is picking teammates for her flag football team. She picks 3 girls for every boy. So part A, complete the table below to show the relationship of boys to girls on Julie's team. Take 1 minute and do that with your neighbor. So it does tell us that it's 3 girls for every boy. So if there's 1 boy on the team, there would be 3 girls. Now if we double the number of boys, then we're going to double the number of girls as well. So for 2 boys, there should be 6 girls. So if there's 9 girls on the team, so we're kind of multiplying the boys by 3 to figure out how many girls there are on the team. So if we wanted to figure out how many boys, we would divide the 9 by 3 to get 3. So if there's 9 girls on the team, there are 3 boys on the team. And then if there's 4 boys on the team, 4 times 3 would be 12. We would get 12 girls on the team there. All right then. From the table, we should be able to make the graph of this. Graph the girl-to-boy relationship for Julie's team with boys on the x-axis and girls on the y-axis. Take 1 minute and complete the table. All right, so let's graph this. It does say that the x-axis is representing boys, so we can label that right now as number of boys. And the y-axis is representing girls, so that would be number of girls on the team for the y-axis. At this point, we'll go ahead and scale the graph as well for each line. So I'm just going to say each of these lines represents 1, starting at 0, and we'll start with the boys. So that would be 1, 2, 3, 4, 5 right there. And this goes all the way up to 10, even though we won't need to go that far. For girls, we'll start at 0, and there should be enough that we can have each line represent 1 as well. So 2, 4, 5 right there. 10, and then up to 15. So we've labeled the axes, and we've scaled the graph. So now we'll go ahead and put the points from the table. Let's go and just write these as ordered pairs first. So that's 1 boy for 3 girls on the team, 2 boys on the team, 6 girls on the team, 3 girls on the team, 3 boys on the team, 9 girls on the team, and 4 boys on the team, 12 girls on the team. We can graph these as ordered pairs. So I've got 1 right there and 3 girls on the team, 2 boys, 6 girls on the team, 3 boys, 9 girls on the team, and 4 boys is 12 girls on the team. Okay, so we have these points on the graph. The next question is, would we connect these points?
Yeah, no.
And the answer is that we would not, because you can't have half a person on the team. So, since those values would not exist, we would not connect these points. We would leave it as it is. So part C, find the ratio of girls to boys for several different ordered pairs in the table. So we have the ratio of number of girls to the number of boys on this, and we're going to use these ordered pairs. So just looking at the graph from this, let's look at some of these ordered pairs. So this one is 1, 3, which tells us there were 3 girls on the team and 1 boy on the team. The next one is at 2, 6. That shows 6 girls on the team and 2 boys on the team. The next one has 3 boys on the team and 9 girls on the team. So as a ratio, that's 9 over 3. And then this last point here has 4 boys on the team and 12 girls. So as this ratio that is given to us, it's 12 over 4. So there's something else we should notice about this. All 4 of these fractions is that if we were to simplify all 4 of them, then we would get 3, which means all 4 of these are equal. Now the reason why that's important is because in order for a relationship to be proportional, values have to be equal. Let's demonstrate this. So for example, let's say that this is a sandwich. Maybe you got some lettuce in there and some ketchup with some peanut butter. I don't know. Okay. All right, what I'm going to do with this sandwich is I'm going to cut it in half. And so this one, I guess this half is given to someone else. Now let's look at this. Right now I have 1 out of 2 pieces, which would be the full sandwich. But if I continue to slice this up, is now I've cut this up, but I have 2 pieces out of what would have been 4 pieces of sandwich. But did I change the amount of sandwich I have?
No.
I didn't. And this would represent a proportional relationship because the values are the same. 1 out of 2 pieces is the same as having 2 out of 4 pieces. And if we continue to slice this up, I could have 3 out of 6, 4 out of 8, and so forth. Okay, these are all equal, which is what makes them proportional. All right, fill in the boxes to show the relationship between girls and boys on Julie's team. All right, so we have these boxes right here, and we can tell from the table, and we should be able to tell from the graph, that I'm taking the number of boys on the team, and I'm multiplying it by 3 to get the number of girls on the team. And we can kind of see over here that, actually we'll get into that. Also, if I take 2 boys on the team and multiply it by 3, then I get 6 girls on the team. So up here where it says 3 times something, that would be multiplied by the number of boys on the team. And that would give us, or it equals, the number of girls on the team. And we could rewrite this as a formal equation because we know the girls represent the y values and the boys represent the x values in the graph and in the table. So in other words, this would be y equals 3 times x as a formal equation for this. Part E, use the equation and graph to determine how many girls would be on the team if Julie chose 10 boys to be on the team. Take 1 minute and do that with your neighbor, and do F as well. We'll go over both. So I'm going to use the equation that y equals 3x, and y represents the number of girls on the team, x represents the boys. For part E, it tells us specifically that its number of boys on the team is 10. So I'm going to replace the x with 10, which means my new equation is the number of girls will be equal to 3 multiplied by the 10. And that then would be 30. So y equals 30, but y represents girls. So that would be 30 girls on the team if there's 10 boys on the team. Part F, use the equation and graph to determine how many boys are on the team if Julie chose 18 girls. So on this one, girls is 18, which is our y value. So I'm going to replace the y with 18, and this will equal the 3x. So this is an equation that we can solve, and it's kind of like the last step in the switch and stay game where we're just going to divide both sides by the coefficient, which is 3. So x would equal 6. And we'll label this, because it is a word problem, x representing boys. So it'd be 6 boys on the team if Julie chose 18 girls on the team. Now before we move on, we may want to look at this. Remember that we can multiply the number of boys by 3 in order to get the number of girls. If we look at it in the table over here. Now what this shows us is the number that we can multiply the x values by, because boys represents x and girls is representing y. That is what we call a proportional constant. Now the reason this is a proportional constant is because no matter what x value I choose, like I could choose 15 boys on the team, I would multiply it by that same proportional constant to figure out how many girls would then be on the team. So the proportional constant is the value that we multiply the x's by in order to get the y values, assuming that the relationship is proportional. Now you guys look at this a little bit differently in 9th grade, but for now that's what we want you guys to know. Especially in the tables, you multiply the x values, it should be the same value each time, which is why it's constant. And then you will get the y value that corresponds with that x value. And this is pretty much saying the same thing. So you guys have already seen this before from 6th or 7th grade. In the previous example, the two quantities of interest are in a proportional relation. Recall that when two quantities are proportionally related, the ratio of each y value to its corresponding x value is constant. This constant is called the constant of proportionality, or proportional constant. The ratio that related the number of boys to girls was 3, and that was the proportional constant for that relationship. Number 2, Carmen is making homemade root beer for an upcoming charity fundraiser. The number of pounds of dry ice to the ounces of root beer extract flavoring is proportionally related. If Carmen uses 12 pounds of dry ice, she will need to use 8 ounces of root beer extract. So do part A with your neighbor. Write a ratio or proportional constant that relates the number of pounds of dry ice to the number of the number of ounces of root beer extract. Do that 30 seconds. Go. So this one says that it is a ratio, and we're looking for the word in a ratio. We're looking for a word 2. And that should help us to write the ratio out. So let's go and write that out. So this is what it would look like as a ratio, formally with the colon in between. But we could also rewrite that as a fraction, which we should have learned in 7th grade there. And we would divide that by ounces of extract. All right, and we do want to see this in more of a fractional form like this one. So let's go and look at what they told us. At the bottom here it says 12 pounds of dry ice. So we know that's 12 pounds of dry ice for 8 ounces of root beer extract. So we've got 12 pounds to 8 ounces. But this one could also be simplified if it were a fraction. And if we were to simplify that, what fraction would we get? So I can divide both by, very good. So if I divided them by 2, I'd get 6 pounds and 4 ounces. Could I simplify this one?
Yes.
Sure it could. What would that be?
3, 2.
Very good. 3 pounds for 2 ounces of root beer extract. Part B then, write a ratio or proportional constant that relates the number of ounces of root beer extract to the number of pounds of dry ice. 30 seconds with your neighbor. Go. All right, let's look at this one. This one, they've changed the ratio. This time it's number of ounces of root beer extract to the number of pounds of dry ice. So let's go and write that as a formal ratio. So this would be the formal ratio. But again, I'm going to write it as a fraction. So this is the fraction right here. And we're going to be writing these ones just like we did for the pounds of dry ice to the ounces of root beer. Okay, so ounces of extract on this one, we already know that it's 8 ounces of extract for 12 pounds of dry ice. And we've already seen the simplified form of this. If we divide both of these by 4, then we should get 2 ounces for 3 pounds. All right, so we have the two different ratios which we'll be comparing and using in the problem. Notice that the proportional constant depends on how you define your items. So part C, complete the table to show the relationship between number of ounces of root beer extract, X, and number of pounds of dry ice, Y, needed to make homemade root beer. All right, take 1 minute with your neighbor and complete this table. So in this table, the nice thing is they gave us something to start with. That's 8 ounces of root beer extract. And we know for 8 ounces of root beer extract, it would be 12 pounds of dry ice. So I know that I can put a 12 in right here. Now, if these are all proportionally related, which they are, and they told us these were constants of proportionality on these. So, I can see the 6 and 12 on the right side of the table there, 4 pounds of dry ice. And I know to get from 12 to 6, I would be dividing 12 by 2. So I'm going to do the same thing to 8. I would divide it by 2. And then I would get 4 ounces of root beer extract for 6 pounds of dry ice. Now 4 and 3 are maybe a little bit more difficult to relate to, and that's okay, because I can relate 4 and 2. I would take 4 and divide it by 2 to get 2 ounces of root beer extract. But again, I don't want to change the values of these as a ratio, so I'm going to do the same thing to 6. I would also divide it by 2, and I would get 3 pounds of dry ice for 2 ounces of root beer extract. If we continue this further, to go from 3 pounds of dry ice to 1.5 pounds of dry ice, then I would take the 3 and also divide it by 2. So I'm going to take the 2 and also divide it by 2, which would give me 1 ounce of root beer extract for 1.5 pounds of dry ice. Now the 1 is really easy to work with, and I know that its relation with 3. So if I take 1, I would multiply it by 3 to get this 3. So I'm going to do the same thing with 1.5. I would multiply it by 3, and that would be 4.5 pounds of dry ice for 3 ounces of root beer extract. So this is kind of like scaling a fraction the way that we want it to. The last one that we want, though, is this 0. And to figure that one out, what I'm going to do is use the proportional constant. All right. So the question is then, what would I multiply 1 by to get 1.5? 1.5. What would I multiply 2 by to get 3? 1.5. So I can see right here that my proportional constant is 1.5. So I'm multiplying all the x values by 1.5. And I would multiply 0 by 1.5 to get that y value, which is 0. So if you have 0 ounces of root beer extract, it would take 0 pounds of dry ice to make the homemade root beer. Take 1 minute with your neighbor and graph the relationship. Okay, in the table they told us that X is the ounces of root beer extract right here. So I'm going to label the x-axis as ounces of extract. And they also said that the y value is pounds of dry ice, so I'm going to label that one as well. And from here we'll go ahead and label the scale, or number the scale. So for this one I can make each line go up by 1 again. Alright, and yeah, the y-axis starts with 0. And from here we'll go and graph these points that we have from the table. So starting with 0, 0. And then 1 was 3.5, so that's 1.5 rather, which is right between 1 and 2 for the 1 value there. And then 2 was 3 pounds of dry ice, and 3 ounces of extract for 4.5 pounds. 4 ounces of extract for 6 pounds would be right here. And then 8 ounces for 12 pounds. Looks like it's up here. So the next question for the graph would be, do we connect the points? So in other words, can we have fractional values of ounces and pounds?
Yes.
Yeah, we can. So in this case, we would be connecting the points. All right, so there we go. There's our line. There's our graph. Very nice. All right, what is the proportional constant for this relationship? Take 30 seconds and do that with your neighbor. What is the proportional constant? So again, it's what are we multiplying the x's by to get the y values, right? Now we've seen that already. So for example, what do I multiply 1 by to get 1.5? 1.5, right? Do I multiply 1.5 by all the values? Yeah, if I multiply 4 by 1.5, that's 6. And if I multiply 8 by 1.5, that's also 12. So our proportional constant is 1.5. All right, take a minute and write down the equation for this as well, for part E. All right. Well, here's what we know, is that the number of pounds of dry ice is represented by the y value, and the number of ounces of root beer extract is represented by the x value. Now, from the proportional constant that we just figured out was 1.5. And we know if I take 1.5 multiply it by any of the x's, then I get the y value, or the number of pounds of dry ice. So this right here is what would represent the equation. Now they're going to show it as y equals 3/2 x, and that would work as well if you want to show the fraction. Every ratio has an associated rate. Unit rate is another way of interpreting the ratio's proportional constant. The statement below describes how unit rate defines y and x in a proportional relationship. If quantities y and x are in proportion, then the unit rate of y with respect to x is the amount of y that corresponds to 1 unit of x. If we interchange the roles of y and x, we would speak of the unit rate of x with respect to y. All right, again, this would be kind of a review for you guys. Let's look at that last problem. So in this problem, the unit rate in this one would be the proportional constant as well. And for that one, we know that it was 1.5 for this one. Now, as a unit rate though, that would be 1.5. It would be pounds of dry ice. And it is a rate, so we want to compare this with another value. That would be for every 1 ounce of root beer extract. So what would the unit rate be if we interchange the roles of x and y? We're just going to flip those two. So there we go. We just reciprocated that fraction by interchanging the rules. Now, one of the things we need to keep in mind for unit rates is that one of the values has to be 1, whether it's the ounces of extract or even the pounds of dry ice. For our purposes, though, we generally want the x value to be 1, which in this case was ounces of root beer extract. Let's look at rate of change a different way as well. So if we were to look at this as a unit rate, then I would be looking at the table. For example 1, if I added 1 ounce of root beer extract to get the 2 ounces, then I would have to add 1.5 pounds of dry ice, which would give me 3 pounds. Well, if this remains constant, then it is the unit rate. So there's another ounce of root beer extract, and there's another 1.5 pounds of dry ice. And this pattern would continue, even though for 4 to 8, it adds 4 ounces of root beer extract for 6 pounds of dry ice. But as a ratio, these are all the same. So that's 1.5 divided by 1 is the same as 6 divided by 4. All right, number 7. Doug is pouring cement for his backyard patio that is 100 square feet. The cement comes out of the truck at a constant rate. It is very important he gets all the cement poured before 12 o'clock noon, when it gets too hot for the cement to be mixed properly. It is currently 11 a.m. and he has poured 75 square feet of concrete in the last 3 hours. At this rate, will he finish before noon? We're going to use the questions to answer that question. Part A, fill in the missing items in the table. If X represents the number of hours that have passed since Doug began pouring concrete, and Y represents the amount of concrete poured. All right, take 1 minute and complete that table with your neighbor. So if we have 75 square feet of concrete poured in 3 hours, then we should be able to find it for 1 hour pretty quick, okay? So that in that case, we would take 3 and we would divide it by 3. But if we do it to that one, in order to scale it properly so it's proportional, we'd have to take the 75 and divide it by 3, which would be 25. So that means after the first hour, then Doug had poured 25 square feet for concrete. Now we could also just kind of assume and look at this. Of course, if 0 hours have elapsed, then we would expect there to be 0 square feet of concrete that have been poured. Now the good news about having 1 hour for 25 square feet is that's telling us the rate. So if he's pouring for 2 hours, we're going to double the 25, and that would be 50 square feet of concrete. Also, if we double that, if we double the 2, then we get 4, right? If we multiply that by 2, so we can multiply the 50 by 2, and that would be 100 square feet in 4 hours. All right, graph this relationship then. 1 minute with your neighbor, go. All right, let's do the graph for this one. In the table, they tell us that the X is hours or time elapsed, so I'm just going to label it as hours. And the Y represents the amount of concrete poured in square feet, so we'll have that as square feet. Then we need to number the lines on the axis. So for the x-axis, we only went up to 4 hours, so we'll just say each one of these represents 1. And this one goes up to 5, not that we'll need it. However, for the y-axis, this one needs to go up to 100, and there's 10 of these lines, so I'm going to say each of these represents 10. All right, now that we have that, we can go ahead and graph these points on the graph. Okay, so we got 0, 0. Then I got 1 hour at 25, so right between the second and third line for square feet. And then for 2 hours, it was 50 square feet. 3 hours was 75, so again, I'm right between those lines. And 4 hours at 100 square feet. Now then, would we connect these points? Yes, we would, because you can have half an hour, and you can have half of a square foot as well. So we will connect these. All right, there we go. What is the unit rate for this relationship? In other words, how many square feet of concrete can Doug pour in 1 hour? 30 seconds for this one. So this one would be 25 square feet of concrete for every 1 hour poured. Now you could show that as a fraction too if you wanted. All right, which equation given below best describes this relationship? Take 15 seconds for that one. So y, which represents the amount of concrete poured, is always going to equal 25 square feet poured for every 1 hour. So we'll just multiply that by the number of hours, and we would have however many square feet was poured. Will Doug finish the job on time? Yes, he will, because at 11, he has 75 square feet poured. He only needs another 25, and we know he can do 25 square feet in every 1 hour. So he'll finish right at 12. Even though it said before 12, it'll be right at 12, so he'll be finished, okay? All right, so the answer is yes. is it proportional? Let's look at graphs for this next one, right? So if a graph is proportional, then it has to be a straight line that goes through the origin. In order for a table to be proportional, then all of the y values divided by the x values have to be the same value. Number 10, Vanessa is mixing formula for her baby. The graph given to the right describes the relationship between the ounces of water to the scoops of formula to make a properly mixed bottle. Part A, does the graph describe a proportional relationship? The answer is yes, because we have a straight line that goes through the origin. Part B, what is the unit rate for this relationship? Show on the graph how you can see the unit rate. So to find the unit rate on the graph, what we need to do is identify two ordered pairs on the graph. And I'm looking at this one. That's 1, 3. And it wouldn't matter which other one we use, but we can use this one as well. That's at 5, 15. Okay, so we want the unit rate on this one. And between these points, from 3 to 15, it increased by 15. And then this way, to the right, it went to the right, so that's in the positive direction, 4. I said 15 on that last one, that's not 15. It's 12. There we go. So it went up 12, and to the right 4, which gives us a unit rate of up 12, and to the right 4. And if we want to label these, the upwards direction is in ounces, which we can see on the graph, and to the right, that's in scoops. Yeah, this is part B, but this one is not a unit rate because neither of the values is 1. For this specific unit rate, we want the x values, which in this case is scoops, to be 1. So I have 12 ounces for 4 scoops. This would be the same as 3 ounces for 1 scoop. Now since this is proportional, we can see that the unit rate can also be found by just finding the x value that's 1 in the point, and its y value is the unit rate, 3. 3 ounces for 1 scoop. Alright, see, at a different location on the graph, show and explain how you can find the unit rate. Well, the only reason we could do this is because it's proportional, but I'm going to use this point. This one is at 412. So the unit rate would be comparing ounces to scoops. And this one specifically has 12 ounces for 4 scoops, which if we simplify would be the same as 3 ounces for 1 scoop. So there again is our unit rate, but we found it by using a point, which we'll have to do on the next problem as well. Part D, write an equation to relate the ounces of water to scoops of formula. Alright, in this one we can see that the y is represented by ounces, so the ounces should equal something to do with the scoops, which is our x values right here. And what are we going to do with the scoops in order to figure out how many ounces are required? You're going to have to multiply it by 3. 3 for this one. Okay. Which is the proportional constant, and it's also the unit rate for this one. And this would give us the equation for this problem. Part E, how many scoops of formula must Vanessa use to make a 9-ounce bottle for her baby? We can use the graph on this one. That's 9 ounces right there. How many scoops would this point be on that line?
3.
Yep, 3 right there. So that would be 3 scoops. Number 11, Ben, Boston, and Brighton have each designed a remote control monster truck. They lined them up to crush some mini cars in the driveway. The lines on the graph below show the distance in inches that each monster truck travels over time in seconds. So we're going to do part A. Brighton states that each truck is traveling at a constant rate. Is this statement correct? Why or why not? Take 1 minute and write the sentence for this one. Talk about it with your neighbor as well. Go. All right, here we go. So Brighton's stating that they're all traveling at a constant rate. If that happens on a graph, then it's a straight line. So this one, the answer is yes, because all three are represented by straight lines. Part B, what do the values in the ordered pairs give on the graph represent? For this one, each ordered pair is an x and y value, and we can see that the x is represented in seconds, and then each y value is represented in inches. So for these ones, Ben's, this one would be 4 inches for 1 second. Brighton's, this one is 8 inches for 6 seconds. And then Boston's is at 2 inches for 4 seconds. And that would be representing each of the 3 ordered pairs that they gave us. Part C, find the unit rate for each boy's truck. Take 1 minute and do this with your neighbor. Find the unit rate for each boy's truck. Now these are proportional, so we should be able to use the ordered pairs to do these. The unit rate for each boy's truck on the graph, if we kind of zoom in on this thing. So we can find the unit rates where x is 1 on these because they're all proportional. So this one up here is already given to us as 1/4. But this one we can't tell, and this one we can't tell unless we have these ordered pairs. Now the good news is we've already defined, we can find it in a table. It's the same way in this with ordered pairs. To find the unit rate, we're going to take the y value, which in this case is 2, and divide it by the x, which is 4. And if we simplify this, we get 1/2. So in this case, the 1/2, that's going to be represented by inches for every 1 second. So that would be the unit rate for Boston, it looks like. And we already have Ben's. Ben's is 4 inches for every 1 second from this ordered pair here. But we got to do Brighton's as well. Brighton is going at 8 inches for every 6 seconds. But we want to know how far it is, how many inches it is for 1 second. So I'm just going to divide the 8 and the 6 by 6. And that would be, so it looks like Brighton's will go at 4/3 inches for every 1 second. Which boy's truck is moving the fastest? 30 seconds with your neighbor, go. Which boy's truck is moving the fastest? Ben, very good. Ben's is going more inches for every 1 second. So this one would be Ben's. And number 12, explain why the graph of a proportional relationship makes a straight line. It's because all proportional relationships have a constant rate of change, which is what makes a straight line. So this also means that if we ever find there's not a constant rate of change, it would not be a straight line. It would be curvy or just kind of jacked up. Summarize what you know about proportional relationships using bulleted list in the space below. Bam, we did it. Proportional relationships are characterized by a proportional constant that relates x to y.
Did we write that down?
And a unit rate describes a proportional constant by indicating the amount of y that corresponds to 1 unit of x. And finally, the graph of a proportional relationship is a straight line that goes through the origin. So the objectives was, I know how to find a proportional constant, and I know how to tell if a table and graph represent proportional relationships, which is kind of what that last one said.